My plan is to finish up Chapter 17 this week, and so what that means is we'll have the test on Chapter 17 next week, probably on Thursday. So Chapter 17 exam next week, Thursday. Homework will be due then as well, so make sure you get your homework in. Homework's worth a lot, 10 points. All right.
I think we were on equivalence point
Okay.
plus one drop.
Equivalence point plus one drop. Did we finish the calculation, or we're still working on that calculation?
I don't know, I might have been doing it solo.
Okay. All right. Do that. We'll finish that. Calculation. But before then, this is important. I'll put a reminder tomorrow, but I have an appointment on Thursday afternoon. So I'll be here for the morning, and then I have a lunch meeting, but in the afternoon I'm going to have to miss. And so Thursday, you don't have to come to Chem, but can you watch the morning lecture? I'm going to record it on video and I'll post it. And so it'll just be online. This Thursday, no class.
What time is the
Morning class is from 9:45 to 10, or what was it? No, actually morning is 11:30, sorry. On Thursdays, 11:30 to 12:55. Yeah. So again, on Thursday I'll be here for the morning, but I have to miss the afternoon, unfortunately. So if you want, you can come to the morning, it's fine, or just watch the recording. All right. So did we do the solution dilution already? Yeah. Did we do step one?
I don't know if we did it together.
Oh, okay. We'll take a look at this. Let's do this now. So the reaction mixture is going to have a total of 50.05 milliliters. We're going to have 25 milliliters of the acid, acetic acid, thanks, and 25.05 milliliters of the sodium hydroxide. And so that's going to give us a total volume of 50.05 milliliters. So we're going to calculate the new concentration of acetic acid first. It's going to be a 25 to 50.05 dilution of 0.100 molar. And so let's see what that comes out to. Divided by 50.05 times 0.1. And that gives us 0.04995. Just go with 4 digits here to go one extra. And then the sodium hydroxide, we're going to have just a slight excess of the sodium hydroxide. This is going to be 25.05 over 50.05, dilution of 0.100 molar. And that's going to give us what? .0500. We're allowed 3 sig figs, but I'm going to carry 1 extra because of the concentration. And so it goes 4.9, but I'll just go 4 and drop the 9. I'm dropping the 9, but I'm not going to round this up because that would just set up a cascading effect of round off error. So we'll just leave it like this. All right, so we have a slight excess of sodium hydroxide. Now we'll go to our step 1, which is acetic acid plus sodium hydroxide. This I called step I, solution dilution. This is preliminary step that we have to get the correct concentrations for the reaction mixture, not the pre-mixture concentrations. Pre-mixture concentration is 0.100. So this is going to make sodium acetate and water. K for this is going to be very, very large. And so essentially this is just going to go to completion. So we have to look at what the limiting reagent is. In this case, the limiting reagent is the acid, 4995. And the excess reagent is the base, 0.05004. The limiting reagent is completely consumed. We end up losing all of it, minus 0.04495. And this is reacts in a 1-to-1, so we'll end up with 4495 here. Well, 4995, sorry, 4995. So this is going to give us 0.0009, quadruple 09. Okay, what we have left over here is strong base, weak base. Mixture. Now the strong base is this hydroxide. And so hydroxide and water just makes water and hydroxide. So what we're going to do with this is, in our step 2, we're going to have this. Okay, sodium hydroxide. This is optional here, this step 2. Sodium hydroxide is going to make sodium ions and hydroxide ions. And so initially we start off with quadruple 0.09 molar and 0 and 0. And then this is going to be complete. This is a soluble salt. Sodium salts are all soluble. And so I'll call this step 2A, which is optional. And this is going to go to 0, and so we'll end up with quadruple 0.09 molar sodium ions and quadruple 0.9 molar hydroxide ions. Step 2B is a strong base. And a strong base is hydrolyzed water completely. So you have strong base and water. This is going to produce water and hydroxide. And so essentially no change, Kb, strong base. This is optional too. Instead, what we could have done is we could have just gone straight to step 3 in this case. Your book is going to skip these here. And we're going to look at acetate. And the same thing, it's a soluble salt. Sodium salts are all soluble, so it's going to break up. And so 3A would be breaking up sodium acetate into sodium ions and acetate. Acetate itself is a weak base. And so here, let's do this. So over here, I skip this. Sodium acetate goes to sodium ions and acetate ions completely. So if I have 0.04995 molar sodium acetate, I'm going to have 0.04995 molar sodium ions and 0.04995 molar acetate ions. Originally this was 0 and 0. And so this is soluble salt. Soluble salts are all strong electrolytes, and they ionize completely. And so if I have the acetate, now acetate's a weak base, and so we're going to have acetate plus water. This is going to produce acetic acid and hydroxide. Hydroxide is going to have a major impact on the pH here. So initially I'm going to have quadruple 09 molar H2O liquid. HAC is going to be 0. This is going to be 0. Here. So the situation here is this. This would be fine if this were weak base alone, but we don't have weak base alone. And so this is actually wrong here. We're not starting off with 0 molar. We have strong base. And that strong base is going to produce hydroxide. Well, how much hydroxide is it going to produce? And so let's take a look. It's going to produce, actually I got this wrong. Sorry, I got the numbers mixed up here. I'm going to have to correct it. We're going to start off with that much hydroxide, not 0, but we're starting off with quadruple 09 molar. This is from the strong base. All right, this I made a mistake here. This is, we're starting off with this amount of acetate. So it's going to go over here. And that's going to be 0.04995 molar. And then we're going to see how much additional hydroxide we're going to get from the weak base. So the strong base produced this much hydroxide. Will we get much additional? And so we'll do the calculation. Minus X plus X plus X molar. And at equilibrium, we're going to have 0.04995 minus X molar, X molar, and quadruple 09 plus X molar. The Kb for acetate is equal to Kw over the Ka for its conjugate acid, which would be acetic acid. And so this is 1.0 times 10 to the minus 14, that's our Kw. And then Ka for acetic acid is given as 1.8 times 10 to the minus 5. And Kb for acetate comes out to 5.55. We're only allowed 2 sig figs. I'm going to carry 1 extra and not round it. Times 10 to the minus 10. Okay, this is going to equal the acetic acid concentration, which is X, times the hydroxide concentration, which is quadruple 09 plus X, divided by the acetate concentration, which is going to be 0.04995 minus X. We could try the simplifying assumption here. You know, on the bottom it looks like it would work okay, but the top it might not work. But let's try it nonetheless. So this is going to simplify into quadruple 09, and the bottom will simplify into 0.04995. And then calculate X. So I'll do 5.55 times 10 to the minus 10 times 0.04995 divided by 0.123, 4 zeros and a 9. 3.08 times 10 to the minus 367 times 10 to the minus 7.
I got a different
What did you get?
2.77, 10 to the minus 8.
2.77 times 10 to the minus 8. Anybody else? We'll let the third person confirm that. I'm sorry?
Could be rounded.
Yeah, I rounded mine, so that could have screwed mine up. But is the simplifying assumption valid? So which one do we want to take? Do you want to take x over point quadruple 09, or do you want to take x over 0.04995?
Where did you get the 1.8 times 10 to the negative 5?
This one?
Oh,
Given.
okay.
Off that table there. So when we calculate the justification for this, I have two percentages that I can make. I can do this change over this initial or this change over this initial. Which one should I do, the numerator or the denominator? Or does it matter? The smaller percent change or the bigger percent change? I mean, the smaller initial or is that what you're saying? The smaller initial? Yeah. The smaller initial, because that's going to lead to a bigger percent change. So divided by point quadruple 09 times 100. That gives me 0.34%, 342%. The percent change in the denominator will be even smaller, a lot smaller. So it sometimes happens where you'll do a hybrid. For example, let's say the percent change in the numerator was too big, but the percent change in the denominator was okay. Then you might do the simplifying assumption just for the denominator, leave the numerator like this. It'll make the math a little bit easier. And so you could be selective like that. All right. So we get that 3.08 times 10 to the minus 7. So I need 6 zeros, 1, 2, 3, 4, 5, 6 zeros. And then a 308 tacked on at the end. And so this is going to give me point quadruple 90308 molar for the hydroxide. So did the hydroxide change significantly? No, not huge. We got a little bit of additional hydroxide from the acetate. And so the pH of a mixture of strong base and weak acid is primarily due to the strong. excuse me, strong base and weak base. This is primarily due to the strong base. Now, the hydroxide changed a little bit. Does it perturb step 2, the previous step? Step 2 was strong, so it doesn't perturb. I could change this significantly, and it's not going to perturb, so I don't have to worry about simultaneous. Let's just double check if my calculation went okay.
Can you go over perturbing and simultaneous?
Yeah, if the current step adds a significant amount, what it's going to do is it's going to screw up the previous step's equilibrium. But in this case, we don't have to. I mean, the previous step's equilibrium it's just a strong base. And so it's not going to perturb. If I add more strong base, then I'll just have a cumulative total. But if it were weak, let's say the previous step were weak, this step were strong, then that's a problem. And so let's take a look. So if I look at step 1, this is for H2S here. If I look at step 1 for H2S, it generates 0.0001 molar hydronium. Actually, we're allowed 2 sig figs. I should increase the number of sig figs there. 1, 0. All right, that's the amount we left off on step 1. When I go to step 2, now some people got this, some people didn't. Which one is a stronger acid? HS minus with a Ka of 10 to the minus 19, or H2O with a Ka, which is equal to Kw, of 10 to the minus 14? Which one is a stronger acid? It turns out H2O is a stronger acid. And so H2O should generate more hydronium than HS minus. It also depends on the initial concentration. The initial concentration of water is close to 55.5 molar as well. And so rather than doing HS minus, which a lot of people did as step 2, you should do H2O. It's going to generate more. Well, how much more? Actually, I didn't quite finish that. If the change is significant here, X, and it changes the concentration here significantly. Let's say we went from 0001 to 0002. That's a significant change. We just doubled the hydronium. Then what that's going to do is it's going to screw up my K here, because my K, rather than being 1 times 10 to the minus 7, is now going to be 2 times 10 to the minus 7. You know, the K is given in the book, 1.0 times 10 to the minus 7. And so that screws up step 1. If I screw up step 1, that means Le Chatelet shift is going to happen. It's going to shift to the left. The concentration of the products increases, which is the hydronium. If it shifts left, then that's going to screw up step 2. So I end up in a circular argument where I solve for 1 screws up the previous, fix the previous screws up the one I just solved for. And so I'll have this endless loop. To avoid this endless loop, I have to solve this simultaneously. Otherwise, I'm never going to get out of this loop. Now, if X is negligible and there's barely any change, then it doesn't screw up step 1's equilibrium. So it depends on how big my X is here. If the X is significant, simultaneous. If the X is insignificant, then stepwise. Now, if step 1 were strong, then strong is one way only. And so strong is not perturbed by Le Chatelet's principle. So if step 1 were strong and I dumped in a whole bunch of extra hydronium into step 1, then no problem. Does that answer the question for that?
So if you do it out of order and then do like a weaker one before a stronger one, then you're perturbing?
If you do it out of order, There's so little hydronium generated in step 2 and 3 anyway, it doesn't really impact it. And so for this calculation, it didn't make a huge difference. But if you do it out of order, then it screws up the equilibria, because then it could, it still doesn't perturb it, but it would be a bigger perturbation than the previous step. And so the amounts come out off a little bit. So if you did it out of order, I just took a small deduction. 0.3, I think.
That's perturbance, right? What about simultaneity?
Simultaneous. That's like the bonus question here. In this bonus question, I did the calculation, I didn't write it down. Yeah, okay. In this one, step 2, do you know what step 2 for this one would be? Would be KW. And so in step 1, you generate like 10 to the minus 9 molar. So 3.11 times 10 to the minus 9 molar. In step 2, you add another like 98. So altogether you'll have 101 parts. And so in step 1, we generate 3 times 10 to the 9 minus 9. Step 1. This is hydronium. Plus step 2. In step 2, we generate 8 times 10 to the minus 80. What was it? 89? No, 98, sorry. 98 times 10 to the minus 9. And so altogether we're going to have 101 times 10 to the minus 9 total. So did step 2 change step 1 by much? Yeah, it changed it by a lot. And so now if you recalculate K, does it still come out to 10 to the minus 10? No, it doesn't. It was 10 to the minus 10 with this amount of hydronium. K checked out. But now all of a sudden we have 101 rather than 3. K is no longer going to check out. So if I calculate K for step 1, it doesn't work anymore. Well, I can fix that. I can fix that using Le Chatelet's principle. Fix it. It's going to, if the hydronium increases, which is product, it's going to shift it to the left. Are you guys following along with this? Or not? Because I'm not writing everything down. Just save time. But do you see how step 2 is definitely going to perturb step 1? It's a huge addition. And therefore, you can't solve this stepwise. You have to solve this simultaneously. Does that answer your question, Andrew, for this? And so for the bonus, you had to solve that simultaneously. So basically, if you set it up, as simultaneous equilibria, like the ice tables, then you would have gotten 4 points for this, if you had set it up. If you actually solved it, the simultaneous equilibria, then that would have been worth 5 points to get the actual value of hydronium. Anyway, I'll post a key for this later.
When you do it simultaneously, do you start with 10 to the minus 7 molar hydronium?
No. You could. That's one way you could do it. You could start with 10 to the minus 7 molar hydronium and then do Le Chatelet's shift. it's possible. That's always, you know, in water, we could always start with this as step one. This is the water equilibrium. And so initially, this is just from H2O. We're going to have 1.0 times 10 to the minus 7 molar. 1.0 times 10 to the minus 7 molar. This is going to be at equilibrium. And then what I mean by Le Chatelier's is this. For step 2, you could do Le Chatelier's shift. And so what we can do here is we can add some additional hydronium to this. When we add the additional hydronium, that's going to change the hydroxide. We can't sustain this much hydroxide. And so it's got to shift it back to the left. And so as we add more hydronium here, that's going to perturb this equilibrium. So what we have to do is we have to go back to this equilibrium and then adjust this one for the additional hydronium. But when we do that, then that changes the hydronium again, and then we end up with this circular problem. We'll have to solve this simultaneously. Does that make sense? You might say, and some people did this, you might say, oh, X is negligible. We have a very small addition. And if that's the case, then you might go, okay, this is okay then. Maybe we could do it this way. Is that what you did, Tristan?
First I tried stepwise,
Mm-hmm.
and then I didn't really understand simultaneous, so I just started out with step 2 right here,
Okay,
and I kind of left it at that.
all right. Well, I'll do the key for this later. All right, so let's go back to our original problem here. And what I want to do is I want to double check my K value to make sure it's reasonable. So X, this one is 3.08 times 10 to the minus 7 molar. And this is going to equal 0.04995 minus 0. And I'll need 6 zeros. 1, 2, 3, 4, 5, 6, and then a 308. And so this is going to be 0.049994692. So let's check these concentrations to make sure that these give us a K value that's equal to this K value here. So I'm going to get 0.000900308 times 3.08 times 10 to the minus 7 divided by 0.049949692. So close. It should be 5.55 times 10 to the minus 10. I got 5.568 times 10 to the minus 10. Seems okay. Really, I'm only allowed 2 sig figs, so both of these are around 5.6 times 10 to the minus 10. Step 4, okay, so this is a base solution. So the strong base, the weak base, and one more hydroxide contributor, which would be water. Should I worry about water? Yeah, what's the most water is going to add? The most hydroxide allowed to be 10 to the minus 7, but it's not even going to be that. It's 10 to the minus 7 in pure water. When we have common ion, the amount is much lower. It's more like 10 to the minus 8. If it was more like 10 to the minus 8, that's not going to really impact this, the pH much. And so we're going to just assume that KW is negligible. It shouldn't be a very large contributor. And so we'll stop here. We'll calculate the POH and then the pH. So take quadruple 090308, take the log of that. I get a POH of 4.044, which is going to give me a pH of 9.955. I'm allowed 2 sig figs, so I'm going to round this to 9.96. So, did we calculate the pH at the equivalence point, which would have been sodium acetate? It should have been like 8.72, 8.72. And then if we go one drop past that, then we're going to be at a pH of 9.96. And then another drop is going to take us way up here. And as we keep adding more, then it's going to flatten out, because now we're going to have plenty of extra hydroxide, and that's going to dominate it. But we also have solution dilution going, so it just climbs up slowly from here. But the calculation would just be the same. Excess strong base and weak base combination. Pretty soon when you're up here, then the weak base is such a minor contributor, because the weak base is going to suffer from the common ion effect. If we have this, you know, the more hydroxide we have to begin with, the smaller our X is going to be. And so as we start climbing up here, we're going to have a lot of excess hydroxide, and then pretty soon we can just ignore the weak base, the acetate. So it's that. So those are the calculations for the different regions of the monoprotic weak acid plus strong base titration. So what we're going to look at next are the polyprotic. Let's take a look at a diprotic weak acid. Plus strong base. For diprotic weak acid, we're going to start at a pH here, say. Then it's going to climb up a little, flatten out. Then we'll have our first equivalence point, and that's going to flatten out. And then we're going to have our second equivalence point. And this will flatten out here. So we expect to see two equivalence points. This will be neutralizing the first proton. And over here, this will be neutralizing the second proton for weak acid. So let's pick an example of some weak acid. What weak acid should we choose? Weak diprotic acid. Carbonic acid, but there's a big problem with carbonic acid. One, carbonic acid decomposes into water and CO2. And so let's say you wanted to make a 0.1 molar solution of carbonic acid. It's hard because what you have to do is you have to bubble the CO2. It's not like you can go weigh. Let's say I need to weigh 1.325 grams of CO2. Is that something that's going to be easy to do? And to get all that CO2 to dissolve in water, is that easy to do? No. So what you're going to be doing is you're going to just be bubbling through a straw, either exhaling, or if you have a CO2 tank, you can just bubble it. But how can you control the concentration? That's very difficult. So when we're dealing with CO2, it's tough. We could try H2S. How do you make a 0.1 molar solution of H2S? That's also tough. Because we'd have to get H2S gas. And H2S gas is extremely poisonous, so we have to take extra precautions so that we don't poison ourselves. And then we have to do the same thing. How can you control how many moles of H2S gas you're bubbling through the water that gets absorbed? Because some of it will bubble out. To avoid that hassle, what we do is we make the H2S saturated. If we make it saturated, then the saturated solution of H2S comes at about 0.1 molar. And so what we have to do is we have to continuously bubble H2S through our solution to keep it saturated, or introduce H2S some other way to keep it saturated. And then that can give us a stable concentration. Otherwise, if we stop bubbling it, then the H2S will kind of leak out of solution, degas, and then concentration goes down. It's like carbonated beverages, What happens if you stop bubbling the CO2, then the CO2 escapes out, and then that's going to decrease the concentration of carbonic acid. So we don't want to use those. Sulfurous is a problem. Although it doesn't show it here, it shows it up on this chart up here. Take a look at sulfurous acid about halfway down, a little more than halfway down on the left side. Do you see in parentheses what it says there? It says SO2 and H2O. And so that means sulfurous acid is unstable. It decomposes into sulfur dioxide and water. So if you try to make a sulfurous acid solution, you can't just weigh a sample of sulfurous acid. You have to take SO2 gas and bubble it in water. It's too hard to control. SO2 is also toxic. And so sulfurous acid is a hassle. Let's pick something easier to deal with. What's easier to deal with? Phosphoric is a lot easier to deal with, except phosphoric is not a diprotic acid. Phosphoric is a triprotic acid. Now, if we have a triprotic acid, what's the difference? Well, in a triprotic acid, we should see 1, 2, how many humps? We should see 3 humps in a triprotic acid, corresponding to the first equivalence point, the second equivalence point, and the third equivalence point. But I'm not going to do phosphoric acid, although your book does phosphoric acid. You know why I'm not going to do phosphoric acid? It's phosphoric acid. Here, this is phosphoric acid, but what's missing? The third hump is missing. We don't see the third hump in phosphoric acid. Why?
So small.
It is. It's so small. And the reason it's so small is because it's so small. We can't see it because in order to see the third hump, we need a pH up here. But you know what the max pH we're going to have with 0.100 molar sodium hydroxide? Well, actually, pure 0.100 molar sodium hydroxide is a strong base. So strong bases, they completely hydrolyze. Well, it's a soluble salt, so we're going to end up with 0.100 molar hydroxide. It's 10 to the minus 1 molar hydroxide. So the power is 1. So the pOH is 1, therefore the pH is 13. So in pure sodium hydroxide, 0.100 molar, the pH is 13. So this is going to max out at 13 at infinite volume, where it's almost pure 0.100 molar sodium hydroxide. It's never going to be pure because of this. We've neutralized some of the sodium hydroxide, but it'll go there. Unfortunately, the pH that we need to see that third equivalence point is above 13, so it's impossible. So one way we might be able to see it is rather than using 0.100, maybe if we use 1 molar sodium hydroxide. 1 molar sodium hydroxide should max out at a pH of 14. So at a pH of 14, we might see it, at least the beginning of it. Or we might have to go with higher than 1 molar, maybe like 6 molar sodium hydroxide. 6 molar sodium hydroxide is going to be at a pH above 14. And if we can get the pH to go above 14, we might be able to see it. So the complication here is we aren't going to see the third equivalence point because to get to the third equivalence point requires a pH higher than what we can achieve with the sodium hydroxide that we're using. So I don't want to deal with this because this is a triprotic acid, but it looks like a diprotic acid, doesn't it? So let's pick a diprotic acid. Here. Preferably nothing too toxic. Oxalic is a good one. Oxalic, unfortunately, is toxic because oxalate forms the oxalato ligand, which is an excellent chelating agent. And you don't want to be eating chelating agents because chelating agents are going to upset the proper ratio of electrolytes in your body. Also, it can precipitate oxalates. You precipitated out one oxalate in the known. Do you recall what oxalate that is? That was? Calcium oxalate. And we have a lot of calcium, so what you can do is you can precipitate out calcium oxalate, which causes, I think, kidney stones. So you don't want a clump of precipitate in your kidneys. And so we're going to avoid that. In fact, you don't want unwanted precipitates. It's hard to model these things, these precipitation reactions. So you got all these equilibria going on. But anyway, if we're careful, oxalic acid's okay. There are some acids that people eat all the time. Citric acid, I like citric acid myself, so I eat citric acid. That's not a problem. Some acids are used in cosmetics, malonic acid. Some are used in food. But anyway, let's go with oxalic acid. Oxalic acid is good because that was the acid that was used in Chem 1A for standardizing the sodium hydroxide. So what you did in Chem 1A was you titrated to the second equivalence point using phenolphthalein. Phenolphthalein, you can see the second equivalence point here. And then use some stoichiometry. Oxalic acid is a solid, so we can weigh it quite easily. And so we're going to go with oxalic acid here. And so I'm going to titrate this. I'm going to use 0.100 molar of sodium hydroxide again. But to make the numbers a little different, I'm going to titrate 25.0 milliliters of 0.200 molar oxalic acid. Okay, in normal titrations we use an Erlenmeyer flask. Do you know why we use Erlenmeyer flasks? Erlenmeyer flasks are a lot easier to swirl. One thing, you can swirl and wash off the insides. That's helpful. And also, it's a lot better at capturing splatter, than a beaker. So the preference is to use Erlenmeyer. Normally, when we have splatter on the inside, that's acid, and we've got to make sure all the acid's titrated. So in a typical titration, we wash the inside walls of any splatter, so all the acid's in the bulk of the solution here. But in a pH titration, we don't wash the splatter because although it won't change the number of moles of acid, it will change the pH. And so in Chem 1A, it didn't matter because the number of moles was fixed, and we never measured the pH. But in Chem 1B, we're measuring the pH, and so we don't wash. And so what we have to do is we have to tilt this, your beaker, and make sure you rinse the inside walls of any splattered acid, otherwise you aren't titrating all the acid. But we've got to figure out where is the first equivalence point going to come in, and where is the second equivalence point going to come in terms of milliliters of sodium hydroxide. So how many milliliters of sodium hydroxide will it take to get the first and second equivalence points? How about the first equivalence point? 25 milliliters? In the last example, it was 25 milliliters because it was an equal amount of acid to base. But in this case, we have twice the concentration of acid. If we have twice the concentration of acid, then what we're going to have to do is we're going to have to double the amount of base. And so the first equivalence point is going to come in at 50 milliliters here. And the second equivalence point is going to come in at 100 milliliters. Well, this is a poorly designed titration. Why is this a poorly designed titration? It's poorly designed because burettes hold a max of 50. And so what I'm going to have to do is I'm going to have to use an extra large burette. One that holds more than 100.
Do we have those here?
No, we don't have those here.
Those are way more expensive.
Yeah. The burettes themselves are already expensive, $100.
I think it's
I don't know what the biggest burette is. I've got to find that. I don't even know if they make a 100 milliliter burette or 150 milliliter burette. You know, but it would be good because the relative error would be smaller, you know, with these huge volumes. It'd be a lot easier to be more precise. All right, so we're going to say this extra large burette, or, you know, hypothetical burette here. Now, the interesting thing is this. The pH at the second equivalence point is going to be above 7, but the pH of the first equivalence point is going to be below 7 here. So that's what we observe in these. And so we got to use oxalic acid here. And we can find some pHs quite quickly. So let's first get the initial pH here. And the initial pH is just going to be undiluted 0.200 molar oxalic acid. Oxalic acid is a diprotic acid. So we have Ka1, Ka2, and Kw. Most of the time, just the first step is enough, Ka1. Sometimes we'll have to do Ka2 and Kw. But let's take a look at the Ks first. Ka1 is 5.4 times 10 to the minus 2. Ka2 is 5.3 times 10 to the minus 5. That just came from the book here. So what do you think? I think just Ka1's enough. Ka2 is 3 orders of magnitude smaller. And because of the common ion effect, it's not going to be so significant. And so if we want just the pH, I think a Ka1 will do it. And so let's go ahead and do that. We're going to have our oxalic acid plus water. This is going to produce hydronium plus hydrogen oxalate. Ion. K for this is 5.4 times 10 to the minus 2. 5.4, 10 to the minus 2, that's kind of big. So initial is 0.200 molar. Then 0, 0. Change, equilibrium. Equilibrium, we're going to have 0.200 minus X. X and X. And so this is going to equal the hydronium times the hydrogen oxalate, that is X squared, 0.200 minus X. We're going to go ahead and try the simplifying assumption. This is going to go to X squared over 0.200, which is going to give us an X value of, so I'm skipping some steps here, try to save some time. And so that's going to be 5.4 times 10 to the minus 2, or 0.054, I should have done that quicker, times 0.2. And then take the square root of that. .1039. Is it okay? No, that's about a 50% change. That's not going to work. Why? Well, the initial concentration was okay, 0.2. The problem was this K. This K is kind of big, 10 to the minus 2. In fact, if you look at oxalic acid's position on the chart there, where is the oxalic acid position? It's right at the border of weak acid and strong acid. And so oxalic acid is borderline strong. That's what we say. And if it's borderline strong, then we expect it to have a high percent hydrolysis or a high percent ionization, and it's close to 50%. Just a hair under 50%. So anyway, we're stuck with the quadratic equation, so let's go ahead and do that then. X squared plus 5 point, actually I'm gonna not write this in scientific notation. I'm just gonna write this in decimal form. Plus 0.054x, okay, minus 0.2 times that, should be 2 point times. Minus 0.0108 is equal to 0. All right, let's plug this into the quadratic solver. So I got 0.054 for B and negative 0.0108 for C. And that gives me an X of 0.08037. So trying this here, it's going to come out to 0.08037. We're only allowed 2 sig figs, but I'm going to carry 2 extra digits to check my K value as a check for my calculation. So I'm going to take these values and double check the K. So it'll be the hydronium times the hydrogen oxalate, 0.08037 squared, divided by 0.11963. And I get a K value of 5.399 times 10 to the minus 2. And so that checks out here. So it looks good. Here, we don't have the answers in the back of the book, so we should have some method for helping us check answers, and this is one way. If you check your answers, then see a mistake, then it's probably just something simple. So you just go back and try it again. All right, I don't think step 2 will contribute much, because in step 2 we go from 10 to the negative 2 to 10 to the negative 5, which is 3 orders of magnitude smaller. And so I'm going to stop here and calculate the pH. .08037. Take the log. .0949. Is that what you guys got? Okay. And so the initial pH here is 1.09. At the start. Now, this first part here we call buffer 1. The reason we call it buffer 1 is because that's what the titration makes. So if we start off with oxalic acid, H2C2O4 plus sodium hydroxide, and here we don't have enough sodium hydroxide. And so what we have is we have a situation where we have excess acid and the sodium hydroxide is the limiting reagent. We haven't neutralized. White, yeah. And so this is going to form sodium hydrogen oxalate and water. And so we're going to have some leftover oxalic acid. The limiting reagent, the LR, is going to go to 0. And so we'll have a mix of oxalic and sodium hydrogen oxalate. This is our buffer 1. All right, and so we should be able to get 5 points easily in buffer 1 region. What's the easiest one to get? I have it in my recording. So if the Ka were this, then the pKa 1 is equal to the negative log of 5.4 times 10 to the minus 2. So 0.054, 1.267. So the pH here is 1.267. That's the pKa. One. And so we should know that in the buffer region, the half equivalence point, the pH is equal to pKa. So this is the pH. All right, 4 more. We should be able to get 4 more pHs relatively easily. What are they? Well, the equivalence point is going to take a little bit more work. Take a Okay, so again, the announcement was Thursday. We're not going to have class. But the recording will be available from the morning. You can come in the morning, and then on Wednesday, tomorrow we'll have lab as normal. I should have blown this up so it's easier to see.
Professor, I sent you my Chateliers lab, what, like, the day it was due. Did you look at it?
Yeah, I got yours. Just others I didn't get. I think I got your Le Chatelier's lab. 2 by email.
They're evil for that. They're evil for that. Oh, two, three, like,
There's like hard Oh yeah.
yeah, oh, that's ever.
Yeah. I told you I was gonna get a bicep motion.
Yeah.
All right.
Cut that.
So I didn't do the 3/4 here. I'm at 37.
Oh, for real? I think we'll look on the trick or treating for like 5 to 10 as well. Everything comes up. Oh yeah, keep going. There's it.